Howdy, in this video we'll start talking about the dislocation imaging in TEM. We will focus on why dislocations can produce contrast and how dislocations look like in TEM. Just one slide on dislocations. From undergrad material science intro level class, you have learned there are three types of dislocations: edge dislocations, screw dislocations, and mixed dislocations. The example on the left is an edge dislocation. You can see extra half plane here and the Burgers vectors pointing to the right. In edge dislocations, the Burgers vector is perpendicular to the dislocation line direction. The example on the right is a screw dislocation, and you can see the Burgers vector pointing into the crystal. In screw dislocations, the Burgers vector is parallel to the dislocation line direction. If a dislocation line has both the edge and the screw components, it will be a mixed dislocation. One thing I'd like to draw your attention to is the local lattice bending caused by dislocation cores. In an edge dislocation, it is here, and in a screw dislocation, it is here. Now, let's look at how dislocation can cause contrast in TEM using the edge dislocation as an example. In bright field TEM images, usually the background will be bright and dislocations will appear to be dark lines. To achieve that, we set up the two-beam condition. The diffraction condition for the matrix will have a small excitation error. Therefore, the intensity of the direct beam will be high and the matrix appears to be bright. However, around the dislocation core, because of there's local bending, locally the diffraction condition is Bragg condition. The intensity of the diffracted beam will be high, and consequently the intensity of the direct beam will be low. Locally it will appear to be dark. And this gives you the diffraction contrast that allows you to see dislocations in TEM. In the video we discussed the bending contours, we mentioned the contrast from bending contours is very similar to the contrast from dislocations. It is similar in the way that the bending, either caused by its own weight of the specimen in bending contours or caused by the dislocation core structure, causes the local change of excitation error value that gives rise to the line features in TEM. Next, we'll discuss what dislocations look like in TEM micrographs. In most of the cases, they will appear to be lines, but in some cases they are not. The boxes I drew here, those are cross-sections of TEM foils. The blue lines represent the dislocation line directions. The green arrows show the electron beam from TEM. In the first case, the dislocation lines are contained in the thin foil. In TEM micrograph, they will appear to be continuous lines. In the second case, the dislocations are inclined through the thickness of the foil. You can see alternating bright, dark, contrast in dislocation lines. This alternating contrast can be explained by both the dynamical and kinematical approximations. In the very last case, you have dislocation lines going parallel to the electron beam direction. In TEM, since we are looking at the 2D projections of the 3D objects, in this orientation, those lines will appear to be dots. This is also the orientation you can do high-res TEM or high-res STEM to resolve the atomic structure of dislocation cores, especially for edge dislocations. It is never too much to emphasize that in TEM we see 2D projections of 3D objects. Same thing applies to dislocations. In the example shown here, both micrographs were taken from the same area but with different tilting conditions. In the micrograph on the left, many of those dislocations, they appear to be long and straight. When we did tilting, we realized these are actually curved partial dislocations on a specific crystallographic plane. You can also see the stacking fault fringes. I hope by the end of this video, you have developed a good sense on how dislocations look like in TEM and why you see dislocations in TEM. In the next video, we'll discuss how to set up a good two-beam condition to acquire dislocation images and the G.B visibility and invisibility criteria.